Well, hey there, HVAC pros and enthusiasts. Are you ready to take your skills to the next level? The HVACR Learning Network has just launched an exciting new e-learning course, High Performance Heat Pumps. And guess what? We're giving you free access to the first 2 chapters. Whether you're in the field, training for that next step, or simply want to sharpen your expertise, this course is packed with everything you need to understand and master high-performance heat pump systems, especially inverter-driven cold climate heat pumps. And the best part? You can access it anytime, anywhere, right from your favorite mobile device. It's HVACR learning made flexible and convenient for you. So what are you waiting for? Click the link. Dive into the HVACR Learning Network and start your free trial today. Your journey to HVACR mastery begins here. Well, hello, HVACR community. Thank you so much for hanging out with us once again. We're going to do some very deep diving into inverters today, and we're going to break down how they function and get down into the weeds of what's actually going on inside of an inverter. Most of our programs are already starting to build their arsenal of inverter-operated equipment. And as educators, many of us didn't work with those in the industry. And so we've got to get comfortable with the technology so that we can better deliver that to our students to prepare them for when they see these out in the field. Now, let us know where you're joining in from. If you have any questions and comments along the way, we'd love to be able to answer them for you. Merv, thank you for being here.
From the Jersey Show. Or is it the shoe? It looks like a Jersey shoe, Pat.
Now, Eugene, thank you so much for joining us today. I'm sure everyone in the industry is, Todd, thanks for joining. I think you'll really enjoy this. Glad that you got some decent weather out there in sunny California, like normally is this time of the year. Kendrick, thank you for joining us, sir.
What's up, Kendrick?
So, Kendrick, Todd, I'm sure you guys, like myself, know Eugene from the industry for his wealth of knowledge on HVAC and refrigeration and all of the theories that go along with it. He's prepared so many educators for the industry. I didn't know myself until I started working here that there's a whole nother side of Eugene besides the mechanical engineer that we are all familiar with. Eugene also is an electrical engineer and has just as much passion on the electrical side as he does for HVAC. And most people don't know that unless you've been in an electrical program and you've used some of Eugene's curriculum on the electrical side. You're going to see a lot more of that going forward, I know. You might not understand things the way he does. And I'm just so glad we're going to share this. So we got a couple different presentations we're going to be working with today to give you the resources and give you a better understanding of these inverters so that you can successfully implement them into the classroom. So what we're going to be working out of is a program that we put together here a while back called the High Performance Heat Pump Program. And so it is a curriculum for you as an educator to have all the information you need to be able to talk about heat pumps, modern heat pumps. But it's built into chapters so that you can break it down into modular training. There is a link here at QR. Will take you to that first 2 chapter free trial if you're interested in looking at that. But when you go to our resources pages, you'll start seeing the book and you'll see the PowerPoints. And so we're only going to be working with 1 chapter of that curriculum today. Chapter number 2 is a section on inverter operation, where we'll start talking about how an inverter works and the different components of it. And Eugene's going to help dive into these components as we're going through to get that deeper understanding of how these things function. So, Eugene, how are you doing today in sunny Florida?
Oh, I'm doing amazingly well, Clifton. It's always a pleasure to hang with you in front of the camera. I'm usually behind the scenes cheering you guys on, but it's nice to get out in front of the camera a little bit, especially talking about inverters. It's like,
Oh,
when people hear about inverters, they think that's a system. And I think what's really important for everybody to understand is inverter is a control strategy. So we're still controlling motors and compressors and pumps and fun things like that. But inverter strategy is really a control strategy.
sure.
So I think it's important to do this deep dive into chapter 2. Is that one of the 3 chapters that people get?
It is, yeah. So
Yeah.
chapter 1 and chapter 2 is in that free
Awesome.
trial. So you'll get to actually see the interactive e-learning course for this. And then,
Exactly.
of course, if you're interested in the PowerPoints, we have those available for a piece of the instructor resources. But that's exactly right when you mentioned how it's a strategy. I've been building out this barn dominium project now. Getting much closer. We've actually been looking at different appliances and different components for it. And as I'm going through my local big box shops, all I'm seeing is inverter, right? Inverter refrigerator, inverter washing machine. And then you go, wait a minute. An inverter in a washing machine or an inverter in some other product. And many of us think that inverter, you're right, is a system, a HVAC system. It's not at all. It's a strategy. Just when we talk about vehicles, and there's actually a couple slides we'll probably dive into, you could talk about a carbureted engine or you can talk about a fuel injected engine. It's really the same type of dynamics when we're looking at inverter operation. Are we using mechanical controls or are we using solid state controls? Hey, glad to have you here, Stefan. Appreciate you joining us from Canada today. All right. So, Eugene, let's step back for a minute and talk about how we got here so that everyone has an understanding. Like we're going to start high, and I'm telling you, by the time we get down into the weeds, Eugene's going to dive us into transistors and how they work and how these control boards actually produce the types of voltages that we will see.
Oh man, you have raised like super high expectations for me today. Woohoo!
I
But
don't
if we take a step back, I started in this industry in 1980, and back in 1980, air conditioning systems had 2 speeds. They had on and off, or
That's
not
right.
off, OFF, not RF. And so either they ran at 0% capacity or they ran at 100% capacity.
That's right.
And when I talk to students and teachers alike, I always like to give this analogy. And just, picture yourself at a stoplight. The light's red.
Mhm.
There's a car next to you, and you're both waiting for the light to change. And the light turns green, and the person next to you, they floor it, right? They jam on the accelerator and they peel out. They're burning rubber. You could smell the rubber, and the car takes off and it speeds to the next intersection where there's another traffic light that's red. So the operator of the car jams on the brakes, and the car comes to a screeching halt until that light turns green again, at which point the driver slams on the accelerator again, spinning out the tires, leaving rubber on the street. The car is peeling off, and again, getting to the next red light. And then picture somebody else next to that car. The light turns green. The person eases their foot off the brake, gently presses the accelerator, and the car takes off at a nice, smooth, even pace and proceeds to the next intersection at a very slow rate. At the point that car arrives at the next intersection, light changes from red to green, and the car continues to travel. And I ask students and teachers alike to describe what they think is going on. First of all, the wear and tear on the tires, the wear and tear on the engine, the wear and tear on the brake system, the wear and tear on your body as you experience whiplash, as your body is jerking forward and jerking to a complete stop.
Right.
And when we talk about early generation air conditioning systems and heat pumps, that's exactly what the system was doing.
Mhm.
The system, if the system was calling for operation, it was turning on and operating at 100%, not knowing what the difference was between the set point and the actual temperature in the space. All the system knew was it needed to turn on and turn on 100%.
Right.
So our early generation air conditioning systems and heat pumps were really like that first car,
Mhm.
waiting for that light to turn green, slamming on the accelerator, slamming on the brake. Again, a lot of physical wear and tear on the components in the system. And we had a lot of system overshoot. We had a large temperature swing in the space. We had higher levels of occupant discomfort.
Mhm.
Again, it was just more erratic operation. Enter heat pumps that are inverter control. We now are resembling that second car that we were looking at, where you're easing off the brake and gently accelerating. So think about an old PSC motor that we used to install, and we probably see out in the field to some
Mhm.
degree now. That motor experienced lock rotor amperage on startup,
Yeah.
and that lock rotor amperage is roughly 5 to 7 times greater than the full load
The
amperage
run
of the
current.
motor.
Mhm.
So you're experiencing that inrush of current. You're experiencing um, excessive heat, because with the inrush current comes heat, because a byproduct of current is heat.
Mhm.
So the life expectancy of these motors was a lot shorter. So again, transitioning from these on and off, these two-speed heat pumps, on off,
Mhm.
I guess off is a speed, to our newer generation heat pumps, really night and day. A picture a system that ideally would turn on one time. The system would really never need to turn off, and it would simply gradually ramp up and ramp
Mhm.
down in speed to maintain the desired set point in a process that we didn't know what was called, back in the 80s, load matching.
Yeah.
The system is actually matching the load. It's adjusting itself. It's thinking, and in some cases predicting what the needs of the space are and adjusting the controls accordingly. So it's actually kind of neat. We hear a lot about PID controls. So we'll probably chat a little bit about
Mhm.
that, proportional, integral, and derivative. And when we talk about proportional, it's how big of a correction do we need, right? Large error, large correction. The integral portion, or the integral controls, it's a summation of all the errors, plus or minus. And we shoot for a zero. We want
Mm.
to be above set point as often as below. And then derivative controls are predictive. Is saying, okay, this is what the system was doing in the past. And based on past performance, how can we predict what the system is going to do in the future? So when you see the term PID control, it's proportional integral derivative. It's the amount of error, the summation of all the errors, and what's this thing going to do in the future? Right? Yes.
Well, even when we start comparing it to like energy efficiency, when we made those shifts, even if we just talk about a standard vehicle and the difference between using that design of on off versus modulated, think about like a vehicle. Like if anyone's ever purchased a vehicle that has high miles on it, the first question you ask, is that highway miles or is that in town miles? Right? Because of that wear and tear and that efficiency that we put on those. And that's exactly what we're doing when we're using our modulation, right? We're trying to reduce those torque shifts. We're trying to reduce that amount of inrush current and heat. And then we start building these algorithms. And we may dive deep into algorithms if that's a direction that people are interested in. If not, I'll save that for another one and do an entire algorithm course, which I love doing. I love to know how these things actually build, their future run cycles, and it's very intriguing. But it's exactly like Eugene is saying, right? It's going to change the amount of efficiency that we're using along that process. Now, to do that, we're going to have some changes in operational characteristics, right? We're going to have better controls to do that. So this is a good place for us to dive deep into some pieces of the inverter. So we're going to switch between different presentations here as we start talking about it, because the one component that sometimes gets a misunderstood reputation in the industry is the inverter control board, right? If we think about how many, say, furnace control boards people assume are bad because they were improperly diagnosed, well, we can apply that same concept when we start thinking about inverter boards. Very few inverter boards actually go bad, right? Many a times it's our inputs that are affecting the logic of the control. And so we'll get the questions, well, how do those inputs affect that? Well, that's what we want to dive into. How do these things operate? It's not just that they operate differently, it's how do they operate differently? And how can I teach this to my students so that when they encounter these pieces of equipment, they go, okay, I actually do have an understanding of this. So, Eugene, let's just do the inverter board. I know different manufacturers can have this board with different pieces, different components of it, but together they all do the same thing. And many
Yeah.
manufacturers are using one board to do these logics.
And the thing is, when we talk about an inverter board, if you look at our service trucks, what's in our service trucks, even what's in our classrooms, if we're teaching this, we don't have oscilloscopes and we're not checking in, values of individual resistors and diodes and transistors, because a technician wouldn't go to their customer's house and say, oh, your heat pump system's not working. Oh, you have a bad 3K ohm resistor on your circuit board. Oh, I've got one on my truck. Let me repair your solid state board. So if a component on a board is bad, we will typically, and rightly so, replace the board. But the problem is, how do we know if the board itself is functioning or not? Every manufacturer of equipment, like you mentioned, Clifton, is going to have their own proprietary circuitry and devices built into the board. But as you mentioned, each board is doing more or less exactly the same thing, right? And that's an issue. And if you look at boards that are replaced, manufacturer will receive a board back, and in many, many instances, as high as 85%, those boards are perfectly fine.
Isn't that
It's
crazy to
easy.
think about?
So when I'm teaching my students about solid state boards and how to evaluate them, I don't drill down into the workings of the board, because you're not able, using your digital multimeter, you're not able to evaluate the components of that board. And if you look at a board, you're going to see dozens and dozens of electronics components on that board. And you might see a chip, and on that chip, you might have 20, 30, 40 individual components. They might be rectifiers and amplifiers and diodes. So when we don't know what a system is doing, or we don't know why a system is failing, we might very well just condemn the board and say, well, it's got to be the board. So the easiest way that I troubleshoot a board is we break it down into 3 component parts. So are we powering up the board? Here's a question. If you have a light circuit, you have lights in your house, you have lights in your dining room, and the light bulb is not on, and you automatically go and change the light bulb, and you put a new light bulb in the fixture, and the new light bulb doesn't work either. And then you replace that light bulb again, and the light bulb still doesn't work. And you're like, wow, this lighting company, they don't have any quality control. Why do they keep selling bad light bulbs? And then you finally realize that the wall switch was off. So we can't condemn a printed circuit or solid state board unless we first establish that the board is receiving proper power. Now, what does proper power mean?
Mm.
Well, that's going to depend on the manufacturers and the specs of the equipment. What is the proper voltage for that board? So we need to understand what that board is supposed to be powered with. So the first step is really determining that the board itself is receiving proper power. If the board is not doing what the board is supposed to be doing, but you're not powering the board, don't blame the board. Oh, my engine, my I don't have an engine. I have a motor in my car. I don't own gas vehicles anymore. But if my car doesn't start, so let's assume I have a gas vehicle and I turn the ignition and the car doesn't start, the engine doesn't turn over, that would be like me, oh man, I got to replace my engine.
Mhm.
And I replace the engine in my vehicle and I try and start my car and I realize that the engine doesn't turn over again. And then I finally realize, oh, I don't have any gas in the gas tank. So how can we condemn a board if we're not supplying it with the proper voltage? We can't condemn an engine in our car if we're not providing it with gas. So number one, determine that the board is being powered correctly. Number two, we have to evaluate the sensory data. Now that's harder or easier said than done. All right, Clifton's got a slide, I think, at the end of this presentation that shows all the connections on the board for all of these sensors that feed into the board. And every manufacturer has different sensors, and every sensor is going to have different resistance values at different temperatures. And you might have pressure transducers that actually act as capacitors. All right, that's it. That's a session unto itself. You have some pressure transducers that are actually two plates. And when you have pressure acting from the system onto that plate, it changes the capacitance of the device by changing the space in between the plates. So every manufacturer is going to have different criteria for each of their inputs, but we need to evaluate that the inputs to that board are correct. Because even if we power the board correctly and we don't have proper inputs, we can't expect the board to function correctly. So in order to determine if the board is functioning or not, we first have to make certain that we're supplying the board with the correct voltage and that all the sensory, all the input data onto that board is correct. And once we establish that the power to the board is correct and all the input sensory data to the board is correct, then and only then can we evaluate if the board is providing the desired output. So if the power is correct and all the input data is correct and the board is not putting out the desired output, then blame the board. But it's very easy to say, oh, we'll blame the board. It has to be the board because I don't understand the board. I don't know what that little black thing is. I don't know what that little blue thing is with the two wires sticking out of it. I don't know what that black rectangle is with 22 wires or pins coming out of it. So so I created a really neat flow chart for a board. And when I came up with the board with this flow chart, it kind of, I was like, no, this is too simple. I go, this is insulting people's intelligence. But if we take a look at this, and I presented and I gave it to some instructors and they were like, this is ingenious. I'm like, well, it's not really ingenious. It's actually kind of, it is a little intuitive. Okay. Top left is a start, and that's where you start. All right. First question, is the board powered? Right? If the board is not powered, determine why the board is not powered. Then correct the situation. Is the situation corrected? No. It takes you back to correct the situation. Is the situation corrected? No. Correct the situation. You can get stuck in there for hours and hours and days and days. And once you correct the situation, now it takes you back. Is the board powered? Yes. Is the sensory data correct? Are the inputs to the board correct? If they're not, figure out why. Correct the situation. And then once we know our board is powered and our sensory inputs are correct, Then we can determine if the output of the board is correct. If the board outputs are not correct, once we've established that the board is powered and the sensory inputs are all correct, then we can conclude with reasonable certainty that the board is bad and we have to replace it. All right. If the board is powered, if the sensory inputs are correct, if the board outputs are correct, we probably won't be on the job. Then the board is working fine and we're all done. Pat yourself on the back, look somewhere else. We've had issues where, yes, the board's powered, the sensory input was correct, the board output was correct, but they still replaced the board. Oh, I must have done something wrong. No, you didn't.
No,
You went
you
through the
followed.
steps. So it's so funny. I get so many requests for this PowerPoint slide. And it seems very basic, seems very superficial, but we're very, very quick to condemn a system component that we don't fully understand. I knew when I first got into this industry back in the late 1600s, if I had an air conditioning system that wasn't working, I automatically blamed the compressor
Oh boy,
because the compressor was this
it's the
black
heart.
cylindrical thing
It's the mystery.
and it had pipe. I couldn't see inside of it.
hmm
So if the system wasn't functioning correctly, it had to be that. And quite often it wasn't that. But I was good at condemning parts. I was really good at that because I condemned everything. I started in this industry at age 14 and I condemned everything.
hmm
Everything except like the cabinet that the unit was in.
Sure.
Everything inside we got to replace.
Well, and I'm like you. I think that's why it's so important to understand how these function. So if we take that philosophy, right, we take that flow chart, and we know that we're going to be looking for some input voltages and some output voltages, and we're going to be looking for sensory inputs. The beauty of most of these inverters, if it's already ran once, if it's went through commissioning, it already understands what those input values are. Most of them are readable through the system, especially if it's a communicating system. So if we go back and look at what are we looking at for voltages, it is actually very simple to look for the voltages. So remember, we're going to be tied onto a single phase AC control power, supply power, right? Whether it's 240 volt or whether it's 120. I actually have a 120 volt inverter that I don't have it here. It's over at my son's right now. That I can typically
get it.
set out. I know I should have. Getting ready to install it over there. So I'm moving it from one of my demos to actually putting it back into service. But it's a 120 volt inverter ductless system. So if we think about what's happening here, we understand the flow of high voltage. So we ought to be able to check coming into that inverter control board, we're going to have our standard line voltage. If I've got a 240 volt system and I got 120 volts coming in, not the board. Okay. It's a power issue. Now, what happens with that power once it gets into that board? That's one of the things that we're going to hopefully dive really deep in for you today, so you can see what's happening with that power, right? So we come in with our AC power. We're then going to convert that power, right? And we're going to turn it into a DC voltage somewhere along this inverter process. And whether you're working on a 120 volt AC or a 240 volt AC or a 480 volt AC system, what we store in DC is typically in that 130 to 140% of its incoming supply AC voltage. It's very common, right? If I got 240 coming in on AC, I'm going to have approximately 300 volts DC stored at our capacitor banks. And all manufacturers of inverter boards have test points for the DC voltage, the midpoint of our entire control. We have places where we can test the voltage coming in. We have places we can test the voltage in the middle in our DC. And then we'll have a place that we can check the voltage on the output. So if we check our incoming voltage and it's correct, if we check our DC voltage and it is correct, then we actually have the chance to re-look at that voltage on the output. And just like Eugene was showing, if our voltages are correct and our sensory inputs were correct, it's something else that's happening along the way. So let's dive, Eugene, if you don't mind, a little deeper into what's happening inside of that board so that we have an understanding of it. I'm going to jump past this one and get right into, actually, I'm going to go back onto yours. and we get right into what's happening with our current when we're moving into these inverter control boards, because the way you explain this really helps it make sense.
Yeah. So people freak out a lot of times when they hear about inverters, and the issue is when people hear about diodes and transistors, they go, "Oh, that's electronics. That's way above my pay grade."
Yeah.
And if you think about it, an inverter board does three things. It takes single phase AC power and, as you said, converts it to DC. It takes that DC, it's a very rough, rippled DC signal, passes it through large capacitors, smooths it, so we get a nice, solid, continuous DC signal. And then it takes that DC signal and sends it through a bank of transistors where we create artificial three-phase. So it's different stages. So yeah, on the left you can see the rectifier circuit that converts AC to DC. Right in the middle, that bank of capacitors, and then on the right there's a bank of 6 transistors. So the minute a lot of us hear about diodes and transistors,
Whoa.
there's this
Whoa.
apprehension
Scary
to
stuff.
what goes on. And when I'm talking to my students, and even when I talk to teachers, I speak about a diode, and a diode is simply just a one-way. It's a check valve for electricity. It lets current flow in one direction and not the other. Okay, that's pretty intuitive because we know what a check valve is. And it gets a little more complicated when we talk about a transistor. And when I'm talking to students and or teachers about transistors, I ask them, I'm like, do you know how a relay works? And they're like, of course I know how a relay works. And this was a discussion I had with my father, because when I was going to school originally and I had a strong electrical background growing up, even before I went to high school and college. And when I was taking my electricity classes in college, I was getting straight A's. I already had a very strong background in electricity. I took my first electronics class and I failed it miserably. If there was a grade lower than an F in electronics, I would have gotten it. And my father was really, really upset because he told me, he goes, "You know this stuff." I go, "But this is transistors. I don't get it." And what I'm going to show you now is a very, very interesting. No, go back. Go back.
Sorry.
Yeah, we're good. Is a very interesting conversation that my father had with me about bridging the gap between electricity and electronics. And the only difference between electricity and electronics is really small compared to electricity. So if you think about a relay, right, a general purpose relay has a coil and a set of contacts. In this case, we have a coil and a normally open set of contacts. And the way a relay works is when we energize the coil, then that set of contacts closes, all right? And now we can see the red line going through, just like that. Watch. Let's see. Got Clifton. There we go. Perfect. We energize the coil, and now the contacts close, and we get current flow. So the coil controls the contacts, and everybody's okay with that.
Yeah.
And when I teach electronics and I talk to my students and even teachers about transistors, I refer to the transistor as a relay. And I teach relays using this. It's a 3/4 inch plumbing tee with a 1/2 inch bolt. And this is how I teach this. And I say, okay, you have a coil and you have a set of contacts. And what I do is I talk about the run of the T being the set of contacts and the bull of the T being the coil. And if you take a look inside, you'll see that there's a wire that's blocking the path. So I have a cross section of it. We can look at the next slide. So this is how I teach transistors. All right. That's a picture of exactly the item I'm holding here. All right. And we have a cutaway of it on the next slide. So if we have the run of the T, which is the vertical path going through, and then the bull of the T is the coil. So right now, there's a wire blocking that path. So if I were to take a ball, for example, and try and drop it through, it wouldn't pass. So there's no path through that T because that wire is blocking the path. All right. So now, if you notice that red line on that illustration, it's a little hinged pivot, very similar to what's actually going on inside the T. So if I put pressure against within the bull of that T, look what happens. I'm going to apply pressure to the bull of that T, and it flips up that piece of wire. So that's physical pressure from the pencil, but on a transistor, we're talking about electrical pressure, voltage.
Oh, sure.
So now we apply electrical pressure to the gate of the transistor, and then we open a path through the transistors of the two terminals, the collector and the emitter. And now with pressure acting on the gate, right, that voltage, if we now try and pass something through, i.e. electrical current,
flows right on through.
We now open the path. So it's funny when I teach the theory of transistors, I'm doing this. Yes, pressure is actually electrical pressure.
Yep.
And the electrical pressure is causing a path to open. Now, inside a transistor, there's no piece of wire that's physically moving. There are no moving parts in a transistor. This happens at the electron level. And it's really not important for us as field technicians to understand exactly how that happens. We could get into discussions on that if we want. But the fact is that when we apply voltage to the gate of the transistor, we then open a current carrying path through the device. So we basically have a relay. We apply voltage to the coil, and then we open a current flowing path. So let's take a look. Because in the portion of our inverter where we're actually taking a DC signal and we are converting it to AC, we're actually creating an artificial AC signal. All right. So if we can hop back to that other presentation, I'll go through that really quickly on how this actually works. So here we got a base and the base collector emitter. The base, that's the bull of our T. Okay. So we apply voltage to the base, and that's going to be voltage across the base and emitter. And once we do that, we then open up that path. So we apply voltage to the base, we open up a current carrying path from the collector to the emitter. And we can control the current flow between the collector and the emitter based on the voltage we're supplying to the base. Okay, so you can shoot forward on that one. All right, so now to create each phase, okay, we have single phase power, AC, converted it to DC, and now we're taking that DC signal and we're putting it through a bank of transistors. And those banks of transistors are made up of series of two transistors connected in basically series with each other. All right. So what we can see is, all right, back to where we were. If we apply voltage to that first gate, G1, gate one, it turns on that transistor as indicated by those red arrows, and that transistor starts to conduct. It turns on. So now current can flow through the collector emitter junction on that transistor G1. And if you look at the output waveform, we now have the transistor turning on, and now it conducts. And then after a certain predetermined period of time, we de-energize that coil. No worries. Go ahead. Boop. Right. And now the transistor turns off. So now we've created that path up. The transistor was on, and now it turns off.
So voltage up and then back to neutral again.
Yeah.
Mhm.
right? And now, once that output voltage hits 0 volts, we then energize the coil on G2, that second transistor in that series, and now that transistor turns on, but now we're working from ground up, so it's negative.
Mhm.
So now we still go, that transistor still starts to conduct, but now in the negative direction.
Yeah.
It turns on, and then we turn G2 off. We de-energize it, and then the output voltage goes back to 0.
So we completed a sine wave
Well,
just
we're
with 2
going to as
switches.
soon as you hit enter.
Oh, okay.
There you go. Boom. So
Yeah, now we're
now,
back.
yeah. So we've created an artificial sine wave. All right. And now if we have 3 sets of those transistors, and we are able to offset the times at which we energize each
Yeah.
of those gates, what we're going to do is we're going to end up with 3 signals that look the same. See, there's transistor 1 and 4. That creates one phase. Transistor 2 and 5 creates a second phase. Transistors 3 and 6 create a third phase. So by duplicating what we've just done, but we offset it by 120 electrical degrees, look what we
Mhm.
get.
Yeah. A 3-phase
Yeah. Hit enter, and I'll show you what we look like.
operation.
All right. All right. Go through. Good. All right. So there's
Number 1
transistor
opens and
1 in
closes.
positive direction. Next is transistor 4 in a negative.
Yep.
Then we energize transistor 2, right? Boom. Transistor 5, transistor 3, and transistor 6. So now we end
Look
up
at
with
that.
this thing. And now that's pretty cool. That's an artificial 3-phase sine wave. So it closely resembles this. Click, click, bingo, right? So now we've created an artificial 3-phase sine wave. So people are like, well, why don't you just use 3-phase? Well, the problem with 3-phase is we can't control the frequency. Yeah, but now if we can control the speed or the time gap in between the instructions that we're giving all the gates, we can change the frequency of the power supply, and that's going to change the speed of the motor, because the speed of our motor is affected by the frequency of the power signal.
Mhm.
So if the frequency, if the time gap in between all the instructions is really, really small, the frequency is going to be high and the speed of the motor is going to go up. Whereas if we increase the time gap in between the instructions, right, that signal is going to spread out. The frequency is going to go down and the motor is going to slow down. I think we got a couple of slides to show that, right? So here's all the instructions. This is what's happening, right? In the order on which transistors are turning on and turning off, all right, which is actually pretty cool. All right, and it's showing what's happening at each 60-degree interval of electrical rotation. But the next slide is going to show you, right, if I decrease the time lapse, the time gap in between signals, I'm going to have a really high frequency because those transistors are going to be turning on and off really, really, really fast. I'm going to have a high frequency and my motor is going to speed up. Like I said, if I increase the time gap in between the instructions that I'm giving each of those gates on those 6 transistors, my frequency is going to be lower and my motor speed is going to go down. So it's actually kind of interesting.
Very
and all
simple,
that,
really.
all that stems from a 3/4 by 3/4 by 1/2-inch plumbing tee.
Yeah. Which we probably have in our classroom somewhere if we look around.
Yeah. What I did with that, I actually drilled a hole through it, and I took a piece of what do you call that?
A dowel rod?
It's actually what the
Roll
hell
pin?
is it? I forget. It's a piece of metal,
Mhm.
and then I took some wire, some 14 gauge
Mhm.
solid wire, bent it around, and created this little flappy thing inside. So it's actually
Genius.
kind of neat,
Love it.
you know. And then what happens is if you put your finger in, it'll actually move the.
Mhm. It'll open our gate.
Yeah, it'll open and close. So kind of neat. If
Yeah.
you've ever been to any of my live sessions, I I carry this with me and pass it around so people can play with it.
Yeah, no,
Yeah,
absolutely.
it's kind of neat stuff. But yeah, so the minute we see electronics, you don't need to be afraid. It's literally just the stuff we know, just on a lot smaller scale.
Yeah. So we apply that back onto that inverter control board, and now it all makes sense what we're doing on that inverter. And so you will see this term quite often, IGBT, insulated gate bipolar transistor. And just understand it's exactly what Eugene is saying. It's a gated transistor. And all we're doing is creating that sine wave. So if I have my incoming high voltage is correct, my DC voltage is correct, and I have an output DC voltage between my three legs, I may not be looking for the phasing, but if I can verify that I have that voltage between those three legs, it isolates what's actually happening within the total system.
Kind of cool, right?
Very simple when we actually break it down. And so many instructors are afraid to introduce inverters into the classroom, not because of the lack of availability of equipment, it's because of the lack of availability of training and understanding how they actually operate. And
Yeah,
that's
and what's
really what we're here
amazing
for.
though, Clifton, is when I speak to instructors and I get to spend some time with them, and the operation of an inverter controlled motor is exactly the same technology that's in
Exactly.
variable frequency drives.
Wait.
A variable frequency drive is a drive where the frequency is variable. It's exactly with so yeah, so that's exactly what it's the same technology that's in a VFD.
Let's look at an ECM. I'm glad you went there because I'd like to bring this exact same topic up. Like, what are we doing on an EC control for our motor? And so it's easy to call that an ECM motor, but it's actually redundancy, electronically commutated motor. And so think about what we're doing with our EC control on the back of an ECM, whether it is a constant torque or a constant airflow, true variable speed. We're coming in with our constant supplied AC voltage. We are converting and storing it in DC. Unfortunately, we don't have test terminals on these, but it's the same principle as
It's
that
your tongue,
inverter
right?
control board. It's right.
It's your tongue.
Just
Is that how you test capacitors?
it's like a 9 volt. So we're going to store our DC voltage, and then we're going to create a 3-phase output. So that's the reason that we have our 3-pin connector running to our motor, because our motor is that 3-phase motor. So when we call this an EC, it truly is a inverter control board. It's the same principle that we're utilizing in our compressor controls. And so when we change and we get that perception, that mentality, we are able to now successfully implement that into our classrooms.
See, it's just like checking a capacitor.
You just got to grab a hold of it and go.
Don't do that, by the way.
Don't do that with 300 volts. It's not going to be fun.
That'll hurt twice.
So if we put that into principle and we understand how that inverter control operates, then it's just a matter of some additional inputs and additional outputs. Think about like an electronic expansion valve. I like to tell people if I have a HVAC system and it has that electronic expansion valve, right? All that we're actually doing is just a metering device. So it's a full standalone operation of the system. A lot of times it's not even tied into that inverter control board. It's tied onto just a separate power supply with maybe some thermistors, and sometimes it uses a transducer for the signal. So if we've got our power is proper through an inverter control board, then it's just a matter of our inputs. Are inputs off or not? Right? If we have movement of our compressor and fan motor but no control, well, then it has to be an input. We've already verified that our inverter control board is functional. It's brought in that AC single phase, converted to DC, and through our transistors created that simulated 3-phase sine wave out that can be checked with a multimeter, looking for that DC voltage on that output. And we can then, if we really wanted to, we can dive into our pressure transducers and our temperature thermistors just to verify their accuracy. but all they're doing is giving us that input that we send back. And I dive into each one of these and what we're operating with each thermistor. If you're interested in learning a little deeper on that, because we're not going to have time to dive into those today because we've covered the control board so thoroughly. But if you go back to that analogy that we started from, it's the exact same principle that we're using in our processor for our fuel injected vehicles. We're managing our outputs from our inputs. We're using a variation of voltages. With our inverter control board, of course, we're going to be manipulating that three-phase voltage, whereas our automotive control board is typically on that single phase. But we do have some systems that have a three-phase output to run fan motors, three-phase fan motors.
And you know what's interesting, Clifton, talking about the automotive side, pretty much all of our cars now, if we're driving any car that's relatively new, they all have this low tire pressure indicator light on the dashboard. They're showing you when your tire pressure is low.
Yeah.
And if you think about it, tires rotate. So if there's a wire connected to your tire, I mean, that wire is getting really, really twisted unless you drive in reverse the same amount of time you drive in going forward. But if you think about how those sensors actually work, right? Those are capacitors that are installed. They're transmitters installed in the valve that goes on your tire, and that pressure transducer is exposed to the pressure in the tire. And as I mentioned earlier, you have a stationary plate on a capacitor, and then you have a variable or a movable plate on a capacitor that is either going to be closer to that plate or further away from that plate, depending on the pressure of the air in the tire. So when the tire pressure drops, that movable plate on the capacitor moves further away and the capacitance drops.
Changes.
And it transmits that information to the board, to the CPU on the board, and it says, oh, the pressure in the passenger side front tire is low. And it could tell exactly what the pressure in that tire is by the capacitance that's being transmitted back to the CPU. And it does that wirelessly, which is actually kind of awesome.
Yeah.
Again, technology is great when it works.
It really is when we understand how to work on those. Chris, that's a great perspective to look at. Thank you for putting that in there. Is when we look at that frequency, it's just a calculation, right? I love being able to look at these. Here a while back, Ty and I were using our little mini oscilloscopes just to be able to look at frequencies like off from remotes and how we communicate. Our world is all about the frequency of operation. And so we have to get our mindset around that. We have to change the way that we present our equipment in the classroom. And that's what we're here to do, is to give you the tools to understand how they operate. I mean, Eugene, think about just those technicians. Like, how did we get good at working on things? We took the time to learn how they operated, and then it became simple.
Well, you know what? Think about even the most simple of appliances we have in our house right now. You have a toaster. Last time I looked inside my toaster, there's still solid state boards inside a toaster. So pretty much anything we're dealing with now has a board in it. And I think we owe it to ourselves and our students and our colleagues and our coworkers and whoever we're working with that we're not fearful of solid state boards. We're still controlling the same components. We're still controlling compressors and fan motors. But the solid state board is just a different means to the same end, and hopefully in a little bit more efficient manner. So what is a solid state board? It's just a bunch of relays and switches and controls, things we're already working with, but they're just a lot smaller. They're relying on, right? If we think about electronics, it's at the electron level. We're talking about movement of electrons through wires, and we're looking at the shifting of electrons, filling holes in doped material to create these layers of N material and P material that we put together to make diodes and transistors. It's a switch, but it's not a mechanical switch. We're not physically moving contacts. It's doing it at the electron level.
Wow.
So you can't see it, you can't hold it, you can't look at it and go, oh yeah, look at those electrons moving. You can't taste electrons moving. Well, you can, but if you taste it, things probably aren't going well for you right now.
Right.
But it's really the same stuff. It's just the manner. It's just the size. We're doing things at this microscopic level, and it's the transistors and it's the electronics that have paved the way for our computers to make millions and millions of calculations a second, because we're not physically opening and closing electrical contacts. We're doing it at a very microscopic level. And that was the conversation I had with my dad. He got mad at me because I didn't understand what a transistor did, but I was able to explain to him what a relay did.
A relay, yeah.
And he's the one who created, I came up with this, but he's the one who created this thing and started talking to me about the pressure, the electrical pressure that's pushing contacts closed, or the physical pressure that's pushing a switch closed, and then I took it and ran with it with this. It was kind of cool, but it really took somebody just to sit me down. And it was literally a 5-minute conversation that my dad had with me. And then after that conversation, I told him, I'm like, well, how come my professor didn't tell me that? He's like, well, your professor is an engineer and they don't typically know which end of a screwdriver to stick in the slot. So they had trouble bridging the theory to the hands-on. And I already had hands-on experience. I already had experience, getting real and feeling and touching and working with things. So it was an easy conversation that he had with me. And then from that day forward, I aced all of my electronics classes, with the exception of that one electronics exam I took that I failed miserably.
Before you
Moving
understood
forward, I was a solid 4.0 student on all things electronics.
Isn't that amazing now?
It was just that one little bifurcation point, that one little conversation that my dad had with me that made it click. And again, with our students, if you're talking to your students, coworkers, colleagues, when that light bulb illuminates, it's a beautiful thing. And you never know when it's going to happen. So it was kind of an interesting discussion. And I was like, well, how come my teacher didn't bridge that gap?
Yeah.
But that's our job.
It is.
As teachers, trainers, colleagues, coworkers, share information.
Yeah, I hope everyone listening and everyone that watches this later gets that out of this conversation, is that we're here to help bridge that gap. Because as educators, whether you're in the classroom or you're in the field, we are all educators of the minds around us, and feeding them quality information is really the goal of all of us. And so this helps me tremendously break down how they operate and to understand that it's not so different than things that I already knew. I just may not be able to relay that information over to those around me. And that's why I love this. When I sat down and was listening to this in one of your classes, I was like, wow, that really does clarify, how things operate, because I already knew what IGBTs were, what their purpose was, but how they function it just didn't make as much sense. And so as we do that, it really it just makes us more comfortable in what we do in the classroom. Yeah, Todd, I hope you really enjoyed that.
No, we're glad.
Yeah,
that's what it's all about. It's all
really
about sharing stuff. You know what, Clifton, what's interesting, when I first became a teacher, I started teaching at age 27, so which was about 38,000 years ago. And I thought that my job as a teacher was to convince all of the people in my room, in my class, that I was the smartest person in the room. And it took me a while, because I was like, okay, well, if I stop talking, people might ask me questions. So I never stopped talking, because I didn't want people to ask me questions. And I just kept rambling and rambling. And then I finally realized, I think it was last week, that hold it, you're already in front of the classroom. They already know you're smart. You already, you've already established the
You're
fact
there for a reason.
that you know some stuff.
Yeah.
So I think it's important, especially for new teachers, to understand that people already respect you for who you are and what you know, and your job is to facilitate their learning.
Mm.
And sometimes, well, actually, for me, most of the time, it involves explaining really, really complicated subjects in words of one syllable. And if you can explain things to your students in simple, easy to understand, basic terms, it's going to click, it's going to resonate. And I think that's the takeaway.
Mhm.
Einstein said years ago, well, obviously he didn't say it recently because he's been dead for a while. So, but
Been a minute.
Einstein had said, if you can't explain something to a fifth grader, you don't know it well enough.
Mm.
I took that to heart because there were some things that I knew or I thought I knew. And I always got really, really technical when I described them. And then I realized, well, you know what? Maybe I don't understand that as well as I think I do or thought I do. So I actually went back and studied and studied and studied
Mhm.
until I learned something well enough that I could really explain the operation of complicated components in a really simple manner. And I hope it benefits you guys. And I really hope that, that you take the challenge. If you find yourself explaining a concept and you're using really, really technical terms that you don't understand yourself, you probably don't understand the subject as well as you would like.
I agree.
So yeah, take this as a personal challenge. Start explaining this stuff to fifth graders
Yeah.
or 5-year-olds.
That's it. Put it in their hands. Show them what this looks like. It really does. It comes down to, Jesse, showing that process and understanding how the human mind thinks. One of the comments that came in actually before this show about this show was someone was looking forward to, this conversation. And I said, yeah, that's really one of the beauty of how things are presented here at ESCO is that we try to take things that have been a challenge and try to repaint them with a new picture. Eugene is wonderful at painting with oil paints. I'm the crayon guy, but we get the message to you in a deliverable concept, right? Take these things that are challenging and make them fun and make them understandable. We did have one question that came in from Paul on testing voltages on these circuits. Should we be using a true RMS meter?
You want me to grab it?
If you'd like to.
Awesome. Yeah. So what happened? So you know what? If you always use a true RMS meter, you can't go wrong.
Mhm.
So some meters use an averaging meter, and averaging meters are really, really good if your signal is near perfect.
Mm.
Once you start getting irregular voltage signals, your averaging meter will not be giving you as accurate a reading as possible. So true RMS meters definitely do cost a little bit more, but they are really, really good, especially working on digitally produced circuits where we don't have a perfect sine wave.
Exactly.
So if you're working on an analog signal where the sine wave is perfect, an averaging meter will be absolutely fine. When you're dealing with artificially generated signals, such as those that we just
Simulated
discussed
sine
from,
waves.
from an inverter circuit, an inverter control board, then you definitely want to be using a true RMS meter. Absolutely. That's a great question.
It really is. Thank you for bringing that up.
Yeah, because basically what a true RMS meter does is it takes its root mean square. It actually breaks that analog signal into pieces, but the signal is already a digital signal if it's digitally produced. So you're incorporating extra errors into it if you're using an averaging meter. And it's just an averaging meter, again, not to get really long-winded, but that's what I'm famous for, is an averaging meter assumes a perfect sine wave, and it goes by the peak voltage, and it calculates a percentage of that, and that's what it gives you. So if you always use a true RMS meter, you can't go wrong. Bottom line.
Exactly. Any other questions, comments before we hop out of here? It's just such a wonderful conversation, and I'm grateful that our community continues to grow and that you're all becoming better educators, better students, better technicians, and it's a wonderful place. I absolutely love what we do here on this show, and I'm so grateful that ESCO has allowed us to continue to grow and develop this. If you have any questions, you want to get a hold of us outside of the show, just give us a call or shoot us a message. We love to hear from you. We love to know the resources that you need to be successful in whatever stage you are at in this industry. Well, Eugene, I don't see any final departing questions or comments. Anything that you would like to share before we hop?
Cell phone number is no. No, I think we covered it. Everybody, thanks for joining us. We really appreciate you.
Grateful to have you all here, and we'll see you all again next week on Did You Know, the ESCO HVAC show. We're going to be on the road next week. We'll be down at the Daikin factory. I should be broadcasting live from there. We're actually going to have Heatcraft on the show, so we have a whole bunch of things happening. A lot of manufacturers we're going to be visiting, staying up to date on changes in technologies and refrigerants, and sharing with you new innovations for our industry. So grateful to have you all here. Eugene,
Clifton, thanks for having me. Always a pleasure, man.
I'm so blessed to be able to know you. I truly love it. Bye, everybody.
Take care, everybody.